Hello, welcome to this video. In this video, we'll be looking at small changes and application of differentiation. So what are small changes? Small changes basically a technique we use to determine the value of a function at a point that's close to 1 whose function value we know. So say this is the curve y is equal to f of x. This is the x-axis. This is the y-axis. And we know the value of the function at the point x, which is y. This is lowercase x and lowercase y. And so we want to estimate the value of the function at a point x plus delta x. Let's call that point x plus delta x, y plus delta y. Now we can estimate y plus delta y to be y, where y is the y coordinate of the point that has the same x coordinate as the point x plus delta x, y plus delta y on the tangent to the curve at the point lowercase x, lowercase y. In other words, at that point there, we can estimate y plus delta y to be y. Now we know that from our knowledge of differentiation, as delta x becomes smaller and smaller, and even you can see it, becomes a better approximation. But as you go further away, as delta x increases, it becomes a poorer approximation. But what is y equal to? We know that y, since that's a straight line, we can use this equation here, that y minus y, uppercase y minus lowercase y, out of x plus delta x minus x is equal to the gradient of the function at the point xy, which is simply dy dx at xy. And so from this we get that y is dy dx times xy, at xy, at the point xy, multiplied by delta x, but then plus the value of the function at the point lowercase x. And so this is how we'll estimate particular expressions. For example, we've been asked to find the cube root of 8.01. Now you know that 8.01 is just 0.01 more than 8, which has a perfect cube root of 2. The function here we're looking at is y is equal to the cube root of x. And our known point on this curve is the point 8, 2. In other words, when x is 8, we know that y will be 2. And so our delta x in this case is 0.01, since it's 0.01 more than x. So our y, which is what we're estimating, is going to be dy dx at the point 8, 2 multiplied by delta x plus y, the equation which we derived on the previous slide. Now, what is dy dx? You know that the cube root of x is the same as x to the power a third. This is going to be a third of x to the power negative 2 out of 3, which is going to be calculated at the point 8, 2, and then multiplied by 0.01, and then we shall add 2 to that. Now what is 8 to the power negative 2? 8 to the power negative 2 out of 3. Once we do that, we're going to get a 12 when we multiply that with a third. 8 to the power negative 2 out of 3 is going to be 1 out of 4. So this will give us 0.01 out of 12 plus 2, which is 2.000833 with the 3 recurring. Now, if you actually used your calculator to calculate the cube root of 8.01, you would get these first 6 decimal places correct. So you can see how good our estimation is because of how small our delta x is. And so that's our of course you could conclude that it's 2.000833 to 6 decimal places. So that's how we estimate the cube root of 8.01. Okay, how about the square root of 25.1? Same steps as in our previous example. The point that we know here is 25, 5. We know that when x is 25, y is 5. In this case, our delta x is going to be 0.1. Okay, how shall we get our y? Our y in this case is the cube root of 25.1. And so anyway, when you get your y, you should conclude that therefore the cube root of 8.01 is this. Because remember, our y is the point on the tangent. Now, the examiner might not know that your y is the point on the tangent. I might assume that your y is in fact the point on the curve. In that case, it might be better to write this as approximately. Since if it's the point on the curve, it's not exactly the same point. So it might be better to write approximately. But I'm not going to use the first example because of the context, since it's immediately following the explanation in the previous slide. But going forward, you might want to use the approximation symbol. This is going to be dy dx at the point 25.5 multiplied by delta x plus the value of y. This is going to be dy dx, since x is the square, sorry, y is the square root of x, which is x to the power half. So this is going to be 1 out of 2 root x. But this is going to be calculated when x is equal to 25. This is multiplied by 0.1, and then we're adding 5. This is going to be 5 plus 0.01, because all this gives us 0.01, and then we add 5, which is going to be 5.01. Now, if you actually use a calculator to evaluate the square root of 25.1, this answer is correct to 4 decimal places. So you could conclude that therefore, square root of 25.1 is 5.01002 4 decimal places. Of course, in questions that you encounter, you might be asked to stop at a particular number of decimal places. And so still then you'd have to use the approximation symbol. But here I'm saying this because I know that this is actually true for a fact. Okay, let's look at a different kind of question where I've been asked to find percentage increase in total surface area corresponding to unit percentage increase in height of a closed cylinder. Now we're told that for this cylinder in particular, the radius is equal to its height. So let's have that in mind. Now we know that the total surface area of a closed cylinder is going to be given by 2 pi r squared, the area of both the circles, plus the area of the middle part of the cylinder, which is given by 2 pi r h. Now because our r is equal to h, and we're relating increase in heights to increase in area, we'll substitute for r with h. This will give us 2 pi h squared plus 2 pi h squared, which is simply 4 pi h squared. So when we find the ADH is going to be 8 pi h. Okay, now we've been asked to find the percentage increase in total surface area. What's the percentage increase in total surface area going to be? Delta A out of A times 100%. That's exactly this is what we're looking for. But how do we get delta A? Now, when we come back to this, delta A in this case is what I'm going to relate to this part. Now this part here is the approximate change in y. We get that the change in y from our estimation is going to be this part here, which is given by dy dx times the change in x. And so to get delta A, we're going to do a similar thing. Delta A will be, approximately dA dH times delta H. Of course, that's dA dH at a certain point. But now we've been told that delta H is, well, we've been told that the percentage increase in height is 1. This is unit percentage increase in height. So how do we find delta H? We know that percentage increase in height is the same as delta H out of H times 100%. So if this is equal to 1%, that implies that delta H is equal to 0.01 H. And so in this case, delta A is going to be the ADH, which is 8 pi H multiplied by 0.01 H. That's going to give us 0.08 pi H squared. And so now how do we get the percentage increase in the total surface area? That's going to be delta A out of A times 100%, like we had stated earlier. Now what's our delta A? It's 0.08 pi H squared, and our A is 4 pi H squared. And I'm multiplying this by 100%. And this gives us 2%. So that would be the percentage increase in the surface area corresponding to unit percentage increase in height. And so this is how we use small changes to estimate what the change in area would be. And so that's how we use small changes in application of differentiation.